Greetings, everyone. I was asked to put together something about the mean value theorem. And so let's get started. First of all, here is the mean value theorem. If a function f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a number c in the open interval ab such that f prime of c equals the quantity f of b minus f of a over the quantity b minus a. So let's try to put this into a couple different contexts. We'll try to put it first into a graphical context, and then we'll put it into a physical context, and we'll try to make some sense of what's being stated here. So let's put this into pieces here, or break this down into pieces. First of all, the right-hand side of the equation here tells us, or gives us a ratio here. It's the change of the outputs over the change in the inputs over some interval. And so you should recognize this as the slope of a line. But to be specific, this is the slope of the secant line to the function f on the interval ab. So if I was to look over here on this graph of this function that happens to be continuous on the closed interval ab and differentiable on the open interval ab, that right-hand side, that quantity f of b minus f of a over the quantity b minus a, that represents the slope of this orange secant line connecting the points a f at a and b f at b. Now if we go back over here to the picture, or rather back to the theorem, the left-hand side here, we should recall graphically, represents the slope of the tangent line to the graph of that f at x equals c. And so f prime of c, we're just finding the slope of some tangent line. But note, we're only told that c is somewhere in the open interval ab, so we know c is not equal to a or b. It has to be more than a, but less than b. And so if we go back to the picture here, the c is not specified specifically in the interval, or it's not given to us. We have to go find it. Now, since we're talking about equal slopes here, where we have the slope of the secant line that's going to be equal to the slope of the tangent line, we're talking about parallel lines here. So there has to be some tangent line that is going to be parallel to the secant line at least once, or at least at one point, rather. There may be more than one tangent line that is parallel to the secant line. I'm going to leave. That's an okay picture. It should be just slightly lower, but for eyeballing the guess there, that's not bad. So that secant line, or that tangent line, is parallel to that secant line, and the value of c looks like it's going to be about right here. Okay, I'll call it c sub 1 because we do happen to have another one. And so the mean value theorem is just telling us, guaranteeing for us, that provided the function is continuous on the closed interval and differentiable on the open interval, then there has to be some tangent line to the curve at this value c, where c is in the open interval ab, such that the tangent line is going to be parallel to the secant line over the entire interval. We have another one which occurs for a negative value of x, and I'm trying to line up my ruler here, maybe do a little bit better picture. It's kind of hard to judge the stylus, and I messed that one up a little bit. The thickness of the stylus against the ruler and trying to hit the tangent point in tangency is a little bit challenging sometimes. That's not quite parallel, but I'm sure you get the point of what I'm trying to make here. This looks like we got C2 somewhere around right here. And so again, the mean value theorem is just guaranteeing that if a function is continuous on the closed interval and differentiable on the open interval, then there is going to be some tangent line parallel to the secant line. Tangent line at some point within the interval, parallel to the secant line throughout the entire interval. Okay, so that's just the nuts and bolts of what this interpretation is graphically. Well, let's go back and start to make a physical interpretation of what's going on here. Well, on the left-hand side here, we should remember that the derivative of a function at c physically represents the instantaneous rate of change of f at x equals c. Excuse me. So this is measuring how fast something is changing. One quantity is changing with respect to some other quantity, particularly at c. Now we should recognize, on the other hand, that the equation over here is our average rate of change of f on the interval from A to B. So another thing that the mean value theorem is guaranteeing for us, provided the function is continuous on the closed and differentiable on the open, is that if you take the average rate of change of the function over the entire interval, then there has to be at least one point within that interval where the instantaneous rate of change had the exact same value. Now, the analogy that I like to use for this would be taking a road trip. So let's say you start someplace over here, and we want to go to someplace over here, and to get there, it's going to require us to travel 300 miles, from point A to point B here. Now, let's say in traveling that 300 miles, it took me 5 hours to do so. Well, what's my average speed for the trip? Well, of course, it would be the 300 miles divided by the 5 hours, and we would get 60 mph, 60 miles per hour. Well, in class, I asked, what does that 60 miles per hour tell us? And after a little bit of thought and discussion, we came to the understanding, I hope, is that 60 miles per hour represents the constant rate at which we would have to travel to complete the same trip in that distance, 300 miles, in the same 5 hours. We know in actuality that we were not traveling. If I was to make this trip, the likelihood of me traveling the exact same speed, 60 miles per hour, for the entire trip is very small, especially when you're going a distance like 300 miles. The obvious thing is I'd have to get in the car first, and unless the car was going 60 miles per hour when I decided to try to get on board the car, which would be quite challenging, the car was probably not going 60 miles per hour when I got on it. So in other words, the 60 miles per hour is just giving the information that if I was to redo the trip, the same distance, the same time, then I would have to do that trip at 60 miles per hour if I wanted to travel at a constant speed. So that's what it's telling us. But let's think about that a little bit more here. If my average was 60 miles per hour, wouldn't that imply that we had to be traveling at 60 miles per hour at least once throughout the entire trip? As my instantaneous speed, I had to go 60 miles per hour at least once. Otherwise, how else would I average 60 miles per hour? Let's make a little bit of an argument here, and we'll appeal to the intermediate value theorem in the process. Let's suppose for a moment that I never did reach 60 miles per hour, that my speed stayed below 60 miles per hour the entire time. Well, remember, an average sort of gives you the middle number. It's not exactly the middle number, but just in one sense, it sort of gives you the middle number of the set. So if my speed never exceeded 60 miles per hour, it was always less than 60 miles per hour, then the middle number can't be 60 miles per hour. And so that would be an impossibility. Now, if there was some way that I started the trip greater than 60 miles per hour and the entire time was moving at a speed greater than 60 miles per hour, then again, my average speed would have to be greater than 60 miles per hour because I never went slow enough to be 60 miles per hour. I can't average something less than, what I'm going if what I'm going is always greater than that value. So if I'm always going greater than 60 miles per hour, my average has to be greater than 60 miles per hour. And this is all, again, assuming that we're talking about a continuous function that is differentiable on the open. So I know I was going less than 60 miles per hour to get in the car. I know at some point if I'm going to average, I'm sorry, that would be a bad argument. Let me backtrack for just 1 second. I got in the car, I was going less than 60 miles per hour. Sorry for the little pause there. So I started out going less than 60 miles per hour when I got into the car. If I'm going to average 60 miles per hour, we're going to, again, I think we understand that we'd have to travel more than 60 miles per hour at some point. And so if I was traveling less than 60 miles per hour, initially, more at some point later, so that I would have the average of 60 miles per hour. Then since the function is continuous, my motion is continuous, there has to be some point at which I was traveling 60 miles per hour by the intermediate value theorem. That's not the strongest argument. I would want to lay it out with some more details with the continuity and the inequalities and all that sort of stuff. But I'm just trying to get you a picture in your mind that in order to have an average of 60 miles per hour, I had to be moving at 60 miles per hour at some point throughout the interval. Otherwise, I would never have averaged that. Again, provided the function is continuous on the closed and differentiable on the open. So there are a couple interpretations here for the mean value theorem. And the first interpretation, as we said graphically, is that there is at least one tangent line that is going to be parallel to the secant line on the entire interval. And the other interpretation is that the average rate of change is going to be, or for the average rate of change, there's going to be at least one instantaneous rate of change that has the same value as well. This is where the title mean value theorem comes into play, because the mean that we're talking about in the title is coming from that word average, as you learned probably many years ago in mathematics, that mean and average in that context are, in a certain context, are synonymous. So that's what we're appealing to. That mean value theorem is giving us some relationship between the average rate of change and the instantaneous rate of change. Go study.